Hello and welcome to my YouTube channel. Today code is related to heartbeat calculation. So before we go into the Matlab coding section, I would like to explain that what is the heartbeat. If you look into the ECG signal, you will find that within one complete cycle there are a few set of waveform. The first waveform that comes is denoted by P. So it is a P waveform, then there comes a Q waveform, and then there comes a sharp peak that is known as R waveform. After that there is an S negative waveform, and then there is a final and last T waveform. These waveforms are generated due to the human heart pumping, blood pumping cycle. Like some waves are generated by the contraction of the ventricle, and some are generated by the contraction and relaxation of the arteries. So the current project is to calculate the number of cycles in a single minute for any ECG signal through Matlab. So we will have to calculate the number of cycles generated by the heart in 1 minute. So beat per minute, it is known as beat per minute. We have to calculate that. So for that purpose I have collected some ECG data. If you look into that, these are .mat files that I have downloaded from a link, and you will see the link over here. I have mentioned the link of the data over here. These are the .mat files. When I execute this code, what happens is that first I have to browse an ECG signal. So I will select the ECG1.mat file. I will load this file and it will show me the original ECG plot, and after that it will apply some low pass and high pass filter on that data, and after that it will do some processing and it will show me multiple set of plots. So I will show the code, and I will with each code I will show the result along with the explanation of the code. So when I load the Matlab ECG signal, then I plot a small section of that ECG signal which is noisy. These are some jitters and sharp noises, high frequency signals, and some low frequency waveforms over here. These low frequency waveforms are generated due to the movement of muscles, like we move our hand and joints and some stops like that. It generates the very low frequency signals, and there are some high frequency signals. These are due to the noise captured by the electrode while collecting the data for the ECG from the patient. So first of all I have to apply a few set of filters like low pass and high pass filters to remove these sharp and low frequency signals from the data. To remove these high frequency signals, what I have done is I have generated a low pass filter. I have applied a low pass filter on that data. So I have created a low pass filter over here. I have added a sampling frequency of 360 samples per second. Hence it has been given over there in the data that this is a 10-second duration ECG signal with total number of samples are 3600. So 360 samples are there in a single second. So I have created a sampling frequency of 360 over here. Then I have generated a filter order. After that I have created the cutoff frequencies, which is 18. So any signal below the 18 hertz frequency will be passed, and other portion of the signal will be suppressed, it will be removed, and it will be filtered out. So after applying these parameters to the Butterworth filter, I have got the coefficient of the numerator and denominator. I have plotted that filter in Matlab. I will show you that how the low pass filter look like in the over here. You can see that 18 gigahertz, here is a cutoff frequency. Below the 18 gigahertz the signal have been filtered, and the other high frequency portion of that signal have been filtered out, and the result of this low pass filtering have been shown over here in this figure. You can see that the high frequency portion of the signal have been removed. Like these are very sharp fluctuations that have been removed, that have been filtered out over here. After applying the low pass filter, I have generated the high pass filter. In these line of codes I have applied the low pass filter on the noisy data to remove the jitter and noises. After that I have generated the high pass filter. Again I have used the sampling frequency of 360, filter order of 10, and the cutoff frequency of 4 Hz. Because I have to apply the high pass filter, I want to remove the very low frequency below the 4 Hz, and I want to remove those frequencies, and I want to filter out the frequencies that are higher than 4 Hz. I have applied these parameters to the Butterworth filter, and the numerator and denominator have been obtained. I have plotted the filtered in the frequency domain. You can see that this is our high pass filter. The frequency below 4 Hz have been suppressed. Like these amplitude have been amplitude of those frequencies have been suppressed, and it is 0 over here, and those which are above 4 Hz have amplitude of 1. So this is our high pass filter. When we have applied that high pass filter on the data, and we have plotted a section of that ECG signal, you can see that these low frequency portion of the low pass filtered signal have been removed by applying the high pass filter. Now there is no any very low frequency data in this filtered signal, so the moment artifacts have been removed over here. After that, what I have done is in order to identify the cycle, I have localized the position of R waveform within this complete set of waveforms in one cycle. I have focused on this waveform which is a peak. The amplitude of this peak is very high, so I have tried to localize these high amplitude peaks within the complete cycle, so that I may localize these beats within the complete set of ECG, and the number of these R waveform in 1 minute will show me that how much is the heart rate of that patient. So the main focus of this code was to identify to localize these R waveform. So in order to identify these R waveform, what I have done is, after filtering the data, I have tried to obtain the peak within these within the hop set of data, like the samples from 1801 to 3600, which is a 5-second duration signal. I have identified peaks within that signal. After calculating the peaks, what I have done is I have created a threshold how I have created a threshold. I have used the same filtered portion of that ECG signal, and I have calculated the RMS value. I have twice the RMS value of that portion of the ECG signal gives me a threshold, and any peak which is the amplitude or which has the value greater than this threshold has been considered as the R waveform, and the location of this R waveform have been identified by using the samples, or using the ones within this array, the R waveforms which have stored the R waveforms. Like you can see that there is a matrix with 50 values, logical, and some of them are ones and some of them are zeros. Like the few values of them over here are ones and the others are zeros. So in order to find the location of these ones within the R waveform variable which have been previously defined, I have used the location and R waveform within the bracket so that these exact location may be identified. After that, I have plotted the original ECG signal, and then I have used the stem plot on the R waveform so that it may be highlighted within the original wave. You can see that within the ECG, which have been filtered by the low pass and high pass filtered, the R waveform peaks have been highlighted with the steric. The stem plot, all other values are zeros except the location of the R waveform. After highlighting the R waveform, what I have done is I have used an equation. I have added all the R waveforms. Like suppose there are 10 R waveforms in the 5-second duration. So the total number of R waveforms within that portion of the signal have been stored in the total number of beats. So I have calculated a total number of beats, which are 6 over here. The total number of beats within the 5-second duration signal have been calculated over here. So the number of beats within 5 seconds have been multiplied with 60 seconds, so that to calculate that how many beats can be there within the 60-second duration. So the results come out to be, if you look into this, results come out to be so the result is 72. So the result is 72. So there are 72 beats within 1 minute duration of that ECG signal. Now I will test some other ECG signal from any other patient, and if you look into the data, I have closed the previous plots. Now you can see that everything is okay. So the heart rate is very high for this patient. It is 108 beats per minute. We'll look into any data for the other patient, and you can see that the same 172 beats are there within 1 minute duration of the signal. So this is all the overview of the code and its output. It was a short demo. So thank you so much. You need to subscribe my channel for the other videos that will come next, and in next uploaded videos. So thank you so much.